Okay, related rate problems are one of the most popular problems for teachers and feared problems for students in calculus. You can tell if a given problem is a related rate because it will contain words like how quickly is blah, 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 blah changing. Okay? No two problems will be alike, but the procedure is exactly the same for all these types of problems. And I use the procedure called the guess method. Okay. G stands for given. So you look for what's given. Then you look for what's unknown. Then E stands for equation. You're going to write out an equation. And S with a star is you need to substitute. You need to substitute. I hope I didn't just unplug this. You need to substitute to prevent unnecessary. When you find the derivative and you have all these different variables. So that's why and then S stands for solve. Okay, so what's supposed to happen is I'm supposed to click on this and you're going to see the story of the ladder. An 8-foot long ladder is leaning against a wall. The top of the ladder is sliding down the wall at a rate of 2 feet per second. How fast is the bottom of the ladder moving along the ground at a point in time when the bottom of the ladder is 4 feet from the wall? So if I click on this, it's supposed to take me there. Put the given information down in the diagram. So this is going to be the given. And here's my ladder. And you can put your planks however you want. Who cares? But it is an 8-foot long ladder. And it's leaning against a wall. The top of the ladder is sliding down. Okay? It's sliding down at a rate of 2 feet per second. So we're going to label this as side X. And the rate, when I'm saying, essentially rate is how much it's changing. So that would be dx dt equals 2. And it's going down, so it is going to be a sign of a negative. So they want to know what it says. How fast is the bottom of the ladder moving? Does everybody see the bottom of the ladder is moving this way? So that we will label, because this is side Y, we're going to label as dy dt. Okay? And that's what we don't know. So I have the given information. We have -2. We have 8 feet. The unknown is what we're trying to find, which is dy dt. We don't know what y is. We don't know what x is. But at one instant in time, we have a picture that looks like this. This is 8 feet, and the bottom of the ladder is 4 feet from the ground. Does everybody see? That at one instant in time, not all the time, just that one instant in time, it's 4 feet away. So I can pretty much figure out what this is. Now, I've done the given, I've done the unknown, so now I need to figure out what equation is like prevailing in this. Sorry? Pythagorean Theorem? Yeah. Okay. So because this is x and this is y, I'm going to say this is, so my equation is going to be x squared plus y squared equals 8 squared. That's all I know, right? Is everybody good with what I did? So this is Pythagorean Theorem, but I know it's 8 squared. By the way, if I label this as z, What is dz dt equal to?
0.
It is 0 because it's not changing, right? It's always 8 feet. It's not changing. Does that make sense to you? I just threw it in there. Okay. So we're now going to do, we're going to DDT each of these things. Do you see everything is related to time? So what I'm going to do is I'm going to DDT each thing. So if I take the derivative of x squared with respect to t, do you remember your implicit differentiation? What do you get? 2x. No, okay, so so 2x, it's not derivative with respect to x, it's derivative with respect to t. So this is going to be 2x dx over dt. Okay, and so I'm going to do this once, and then I'm not going to do it again because then it gets too confusing afterwards. So what I'm essentially doing here, just to show you, I'm taking this equation and I'm DDTing both sides. Does everybody see that? I'm DDTing this and DDTing this side. No, you don't have to. Okay, so here's the thing. I cannot find the derivative of x squared unless it's written as dx squared over dx. Okay? So I'm just going to show you why this works the way it is. So this is now dx squared over dt plus dy squared over dt equals, well, what's the derivative of 64 with respect to t? 0. Okay, so we can actually not calculate the derivative with respect to t because there's no t there. However, I can start throwing some things in there. So for instance, I could do dx squared over dx and then times it by dx and move that dt over. Okay, so I'll show you what I did. Essentially what I did is I said I'm going to do this once just to show you why there's the extra dx dt, and then you'll never think about it again. Does everybody see? Now I can actually find the derivative of x squared with respect to x, and that's how I'm getting 2x. Okay? But then I have this extra dx dt that I have to actually write. Okay? Same with this one. I can't find the derivative of y with respect to t because there's no t there. So I put the derivative dy squared with respect to y, but then I can't just throw that in there, so I multiply it by dy, so these cancel, right? dt. So now when I find the derivative of y squared with respect to y, what do I get? No, it's going to be 2y dy dt. The y prime is when I was finding the derivative of x, and really it was dy dx, and we just wrote y prime. This is with respect to t. We have to put the t there. And so then if this, of course, is equal to 0. Okay, let's go. Do you remember this was my y, this was my z, and this was my x. At this point, I can solve what x is, right? X is going to equal the square root of 64 minus 16, which is what? 48? The square root of 48. I'm trusting the calculations. And then we can simplify that as 16 comes out. Yeah, so 4 root 3. Okay, so we're going to put this in here. So x is, we're at now the substitute side. So 2 times 4 root 3. dx dt was what again? Minus 2 plus 2, what's y? 4. We don't know what dy dt is, but that's what we're trying to find out. So this is what we're trying to solve for. So I'm just going to move this over a little bit so I have enough room. I know. Okay, so now I'm going to do my calculation. What's 2 times 4 root 3 times minus 2? Minus 16 root 3. And what do I get here? Plus 8 dy dt equals 0. I'm going to move the 16 root 3 over, so I get 8 dy dt equals 16 root 3. It becomes positive when it goes over there. And then dy dt would be 16 root 3 over 8, which reduces down to 2 root 3. And this would be feet per, and it's positive, which means it is going, which we knew already, to the right. If it was going to the left, that would be negative. And we don't actually give our answer as negative. We say it's either decreasing, or it's going down, or it's going, you know what I mean? You don't use negative. A boat is being pulled toward a dock by means of a rope attached to the front tip of a bow. Bow of the bow. Initially, there's 30 feet of rope out, and the rope is taut and being reeled in by a circular device on top of, top of which is 10 feet higher than the point where the rope is attached to the boat. This circular device has a radius of 1 foot and turns at a rate of 1 revolution every pi seconds. How fast is the boat moving along the water when there are 15 feet of rope out? So the first thing we have to do is draw a picture. So again, a lot of it has to do with, there's like triangles and stuff like that, right? Okay. So a rope is being pulled by means of a rope on the tip of a bow. So here's my boat right here. I can't really draw a boat, but here's my boat. There's the boat. Okay? And this is the rope right here. Yes? And it's pulling it in. Does everybody see that? But the water's right here, so it's not like it's going to pull it into the air. It's going to pull it closer and closer to the dock. Does that make sense to you? Okay. So initially there's 30 feet of rope out, and the rope is, that's initially, so we can start it as 30. And it's being reeled in a circular device at the top of which is 10 feet higher than the point where the rope, so this is 10 here. So this 30 is changing though. That's the thing. So I don't like putting on initial diagrams things that are changing. So I kind of don't want the 30 to be there because I know it's going to be changing, right? So it's going to be changing a certain amount. This is not changing. Does that make sense to you? And does everybody see when they're pulling in the rope, this is getting, like it's getting smaller, right? So visualize, there's somebody cranking, I don't know what, they're cranking this and the boat is just going this way. Yes? We good so far? Okay, so, what else do we know? How fast is the boat moving along the water when there's 15 rope out? So I'm going to do the instant diagram. Say what?
The circular device
has a radius. I'm just going to put radius. Radius is 1 foot. And turns at a rate of 1. So the thing is this is going to be a certain angle, right? And what they're giving you when it's saying every pi seconds, they're giving you d theta dt. 1 revolution every pi seconds. How much is 1 revolution? 2 pi radians, yeah? 2 pi radians? So if it's every pi seconds, then what would the rate be then? So this is 1 revolution per pi seconds. 1 revolution is equal to 2 pi radians divided by pi. Does everybody see this would be 2 radians per second. And this is going smaller, so this is going to be minus. Okay? The other thing we know is this isn't changing. So if I label this, say, x, or I can label it y if it's going up and down. If y equals this, dy dt doesn't change. Does everybody see that part? Okay, let's do my instant diagram here. There's 15 feet of rope out. So 15 feet, this is my theta, this is my 10. If you want, you can say this is 90 degrees. Does everybody see here that the instant diagram gives me what? It's funny, I'm doing one. So anyways, I have a theta here, but I'm also thinking that this is 1 revolution every pi seconds, and the radius is 1 foot. So if I were to change this into how much this is actually this gap is changing, right?
Maybe we could change it, set it to the rate at which the rope is shortening.
Right, and see, that's the thing. So initially I thought this was like this would be hypotenuse and this would be adjacent, so a cosine thing. But the thing is do you see, it's talking about feet here, and there's no actually degrees here. Do you see what I'm saying? So initially the d theta dt, it shouldn't be. What's happening here is this is actually getting smaller, and that's what we're trying to find, right? Okay, so I like this. This is 1 revolution every pi second. But 1 revolution, how much am I traveling in 1 revolution? 2 pi r. That's what you said back there? And so, because we're traveling in a circle, right? That's what the radius is. So 2 pi r is giving me it's still going to be 2 pi, but instead of having it as radians, it's going to be feet per second.
Yeah, it'll make it easier because that's all.
I'm sorry, Kyle? It is. Okay, so I'm going to explain that again. Does everybody see that this, if you picture this is a big circle. A big circle. And this is coming in, right? So do you see that we have the circumference that it travels all the way around, which is saying the speed is 2 pi r. So circumference is 2 pi r, so this would be 2 pi times 1, and this is per pi seconds. This would be feet, and this would be seconds. So does everybody see? I get 2 feet per second. And if I name this, I like Z, I don't know, do you want C? And so I had this as Y, let's do this as Z. So dz dt is going to be 2 feet per second, but it's going to be minus 2. I'm going to circle that. I'm going to circle that. Okay, are we good so far? So I can figure out this part here. I'm going to call this x. Does everybody see? This would be x. dx dt is what we're trying to find. Does everybody see that? Okay, so I can do Pythagorean Theorem to figure out what x is. I kind of want to use a calculator, but anyways. So yeah, 225 minus 100. So x is the square root of 125, which 25 goes into that. 5 root 5. Okay, everybody good with that? Okay, so now I'm going to go back to the diagram over here, and I'm going to use Pythagorean Theorem. So x squared plus 10 squared equals z squared. Everybody good with so far? 10 squared will automatically take, because this is the changing one. This is what I'm trying to find. So if I do implicit differentiation, I will get the dt's, right? So I'm ddting both sides. Again, I only showed this once, so now you know what to put here. What happens here? We get 2x dx dt. I find the derivative of this with respect to t. It goes away. So plus 0. I'm just going to put a placeholder so you know that it disappeared. And then what do I get here? 2z d. Okay. So now we're going to substitute in.
You actually have to know all this.
Okay. So now I'm going to substitute x in, and I have 5 root 5. And I'm going to, I can't substitute dx dt. That's what I'm trying to find, right? And then z is 15. And dz dt I already figured out was minus 2. Okay? So just to make things easier, well, I can just write it out. dx dt is, I'm going to just keep it like this so I can cross cancel much easier because I don't have a calculator. Does everybody see what I'm going to do in a second? So the 2's will cancel. This is why I'm doing this. The 5 and the 15 will cancel. So then I get minus 6 over root 5. And technically you can leave that as your answer, but I know on your homework it'll be rationalized. So I'm going to rationalize this, which is then root 5 over root 5. So this is minus 6 root 5 over 5. So that means my answer is, what are we actually trying to find? How fast is the boat is decrease. Yeah, but we're not going to use a minus though, right? How did I word it here? I didn't even word it. The distance of the boat is decreasing. How about that?
Distance between the shore and the house?
The distance between boat and dock is decreasing at 6 root 5 over 5 feet per second. Again, I will repeat, we're not using negatives, we'll use the term decreasing. So a lot of the times, say in the multiple choice, they'll actually say, how fast is the boat distance decreasing? And then you wouldn't even have to say all that, you would just say 6 root 5 over 5 feet per second. So it says water is being poured into a conical reservoir at a rate of pi cubic feet per second. The reservoir has a radius of 6 feet and a height of 12. At what rate is the depth of the water increasing when the depth is 6? So just to see this, so it's a cone and it's getting filled up. Do you see what I'm saying? Okay, so there's the visual. Okay, so let's draw a picture here and label. So I'm going to draw a basic cone like this, right? And there's a height, and then we have the water here. Maybe I'm going to make the water like this, so you can tell it's water. Does everybody see? There's the picture. And it says water is being poured into a conic reservoir at the rate of pi cubic feet per second. So this is a change of volume, right? So dV dt, it's a change of volume, right? Is pi cubic feet per second, and it's increasing, right? So it's positive. That's going to be the height of my cone.
No, the middle line, what height is that?
Well, I don't know. I haven't gotten that far. Because the height of the water is changing, right? So, yeah. The reservoir has a radius of 6 feet across. So this is 6 feet. And this is 12 feet. Everybody see that? At what rate is the depth of the water increasing when the depth is 6 feet? So my instant, I hope I didn't undo this. Keep on stepping on it. My instant looks like this. And this depth is 6 feet. This still is 12 feet. This still is 6 feet. And I can actually calculate what this is. Grade 9 math, we learned similar triangles. Grade 9 math, we learned similar triangles. So does everybody see I have this triangle here and this triangle here, and this is 12 and this is 6 and this is 6, and I don't know what that is.
Wait, are we looking for angles of the thing? I'm smaller.
I'm just saying I don't know what that is, and I know I'll have to do that for my volume,
Yeah.
right? Yeah? Okay, so volume of a cone is 1/3 pi r squared h. It's basically the cylinder area and then times it by the height, but then it's 1/3 the amount. Now here's the thing. So we have too many variables here. Does everybody see? No, we know h at one instant in time. We don't know what h is at any point in time. Do you know what I'm saying? That's why I like labeling this instant versus this is the one that is changing. If you want to, you can label it changing, but I always label my instant so I don't get confused between the two.
You just label all the constants on that.
Yeah.
Right. So here's the thing. So I want to get rid of this, what am I trying to find here? At what rate is the depth of the water increasing? So I actually want to calculate dH dt. Does everybody see that? That's what I'm trying to find. So I don't want the r in there. So you're supposed to discover from this diagram something in relation between the height and the radius. So what would you say? Yeah, the radius is 1/2 the height. Does everybody see that? So we're going to substitute this with 1/2 h. So v, and so that's why there was that substitute star. I need to replace this because otherwise this is going to be, you can't find it. You're going to have, it'll be like a product rule with all this craziness going on. So 1/3 pi, this is going to be 1/2 h squared times h. Okay, so then this is 1/12 pi h cubed. Is everybody good with what I did there? A half squared is a quarter times 1/3 is a 12, and then h squared times h is h to the power 3. Now I'm going to do implicit differentiation with respect to t. So what do I get here? I just get dv dt, right? Because I'm ddting both sides, right? These are constants, so I'm just going to scooch it over. So 1/12 pi, and now I'm going to do ddt to the h cubed. So what do I get? 3h squared dh dt. Yes? Okay, now I'm going to substitute in what I know. So at that one instant in time, well, the dv dt is pi. And over here, if you want, you can simplify a few things here, like the 3 and the 1/12 becomes 1/4 pi. And the h, remember what h was? H was 6. So this is going to become 6 squared dh dt. Remember, it's what rate is the depth when it's 6 feet, right? So that's why I'm putting that in there. So the pi's will cancel. Does everybody see that? That's nice. So then I get 36 divided by 4 is 1 equals 9 dH dt. So what does dH dt mean? 1 over 9, is that feet? Feet per, no, it's not cubic because this is depth, per second. And because it's positive, that means it's increasing, right? It's increasing. Okay, so let's draw the lamppost and the guy. Here's the lamppost or the light. And here's the guy. Well, it looks like a sun, but it's a lamppost. And here's the guy. So the guy is 6 feet. That's not changing. And the lamppost is 20 feet high. That's not changing. So I can put that on the changing diagram because it's not actually changing. Does that make sense to you? But he's walking toward the lamppost at 5 feet per second. So the light at the top of the lamppost is casting a shadow. So here's the shadow. I'll put shadow. At what rate is the tip of his shadow moving? And at what rate is the length of the shadow changing when he is 10 feet at the base of the lamppost? So I'm going to do the instant diagram just so we can put some more things on here. At the instant, he is, say like that, more like it. And so his height's still the same. It's still 6 feet, and this is still 20 feet. But it's saying that he's 10 feet from the base. So from here to here is 10 feet, right? So here's something you don't realize, that there's actually, this is changing and the shadow is changing at a different rate. We can go back to the diagram so you could see a little bit better. But so if I call this x and this y, dy dt is actually different than dx dt. Because this is changing, right? But because this is at an angle, this is not going at the same rate. Does that make sense to you? And like I said, I'll show you the diagram again of Homer. Here's Homer. Do you see? They even have the things here. So do you see they're not going at the same pace? Yes? Okay. So what else do I need to put on this diagram here? The 5 feet per second. It says that he's walking towards the lamppost at 5 feet per second. So what is that on this diagram? Yeah, so dx dt is 5, and it's going this way, so it's negative, yeah. And I'm going to put feet per second. Okay. Yes. Okay, so I know this kind of looks like it should be Pythagorean Theorem, but it's not at all. It's actually similar triangles again.
You got the big triangle.
You got the big triangle and you got the little triangle, yeah. Yeah, and so the big triangle's one side is x and y added together, right? So just so you see the similar triangles, we have the big triangle here, which is 20 and x plus y, yes? And then we have the smaller triangle here, which is 6 and y. Yes? Okay, so the way similar triangles works is they're proportional sides, right? Okay, so over here, again, this is grade 9 math. This over this equals this over this. Yes? So 20 over 6 equals x plus y over y. So I'm going to do some cross multiplying here, and I get 20y equals 6x plus 6y. I'm going to move the 6y over, and I'm going to get 14y equals 6x. So I probably want what x equals, right? Because I know what dx dt is. So x equals 14 over 6y, which is x equals, what, 7 over 3, just to reduce it a little bit. Are we good so far? Okay. So this is going to be our equation that we're actually going to be DDTing. Okay? So we can do it like this if you want, or this, or we can do it like this. Do you want to do it over here? It doesn't matter. I just thought this was simpler to look at. So does everybody see if I DDT both sides, I get dx dt equals, I'm going to scooch the 7/3 over, and then I'm going to get dy dt. Interesting, we don't need to know what x and y is in this case. Do you see what I'm saying? Dx dt is minus 5, so minus 5 equals 7 over 3 dy dt. So dy dt is going to be negative 15 over 7. Okay, so this was dy dt. So this was the change of the shadow. So, but the thing together is the change of them added together. So, therefore, the shadow is decreasing at minus 15 over 7 feet per second. And we need to add the two together to get what the tip of the shadow is changing. Does everybody see the tip is the whole thing together moving? Okay? Oh, yeah. Yeah, sorry. This should be 15 over 7 feet per second. Yeah. And, okay, so then we're going to, and the tip is decreasing at a rate of 15 over 7 and 5. So that would be what, 35 over 7. So that is what, 50 over 7 feet per second. Again, they're both decreasing because they're both negative. So, like I said, the last question is pretty fast and easy, actually. A circle starts with a radius of 1 at time 0, so say like that. And then what's happening, it's growing, it's getting bigger, right? It's going out. Yes? So it's saying the area is increasing at a rate. So when they say the area is increasing at a rate, they're giving you dA dt of 2 centimeters squared per second. Find the rate of the change of the radius when the radius is 5. So again, the instant is 5. So we have a circle and this is 5 centimeters. Okay. So does everybody remember what the area of a circle formula is? Yeah, area is pi r squared. So good news, dA, dr, right? There's nothing to substitute or whatever. So ddt both sides, we get dA dt equals, scooch the pi over, then we're going to get 2r dr dt. We know that it is 2 for dA dt. And we do know that the radius, I'm going to put 2 pi, the radius was 5 at the instant that we're looking for, so this would be 5. And we are trying to find dr dt. So if I solve, I'm going to get rid of the 2's, and then dr dt is going to be 1 over 5 pi, and that is centimeters per second. And because it's positive, it is increasing, which you already knew that it was increasing, right? All right.